we are going to discuss about syntax analysis phase. This is the second phase of compilation process, which takes stream of tokens as input and generates parse tree as output. So this syntax analysis phase will identify the syntactical structure of the given source program. So here further it will generate that syntactical structure can be formed by using parse tree. So that for generating this parse tree, we'll make use of context free grammar. This context free grammar, the syntax of a programming language can be described by using context free grammar. This context free grammar will make use of BNF notation for describing the context free grammar. So here the syntax analyzer will take stream of tokens as input and checks whether the syntactical structure, whether it follows the syntactical structure or not. If it follows the syntactical structure, then that will be identified by using context free grammar. If it follows the syntactical structure, then it will generate the parse tree as output. If it is not follow the syntactical structure, then it will generate the error message, and that will be handled by the error handler. In some situations, some of the errors has been generated and which can be rectified by itself, so that those errors will be rectified by itself and it will continue the process. So this is the actual structure of the parser. So first we will take the source program as input to the compiler. So lexical analyzer is the first phase of compilation process, so that it will take the source program as input and generates tokens as the output. Now we are discussing about this parser. So this parser will take stream of tokens. So one token at a time. This parser will take a token at a time and it asks for the next token. So like this, it will take the stream of tokens and generates the parse tree. So here that parse tree will be given to the remaining phase of the compilation process. And this parser is also associated with the symbol table and which has been generated by the lexical analyzer. So these are some functions of parser. Here it checks whether the structure of the statement is correct or not, and that means it generates the parse tree, which can also be called as a syntax tree. And if we are unable to generate the parse tree, then it will generate the errors. Those errors are called as syntactical errors. And it also, by using some error recovery schemes, some of the errors has been rectified by itself. And some issues has been, we may raise some issues by using this syntax analysis phase. Generally, this syntax analyzer or the parser will take stream of tokens as input and generates a parse tree. While we are generating the parse tree, it doesn't consider what type of identifier it is. For example, in the given statement, if there is an identifier, what type of identifier it is, what is the scope of that identifier, all those things has not been considered by the syntax analyzer. That is why that will be taken care by the semantic analysis phase, that is the next phase of compilation process. So in this parser or the syntax analysis phase, just we are checking the syntactical structure. Each and every programming language contains its own syntactical structure for writing the statements in the given program. So it checks only the syntactical structure, whether it follows the syntax or not. It doesn't consider the meaning in the syntax analysis phase. That logic or the meaning of the statement has been considered in the semantic analysis phase. So we are categorizing the parser, that means syntax analysis phase. In the syntax analysis phase, we are generating the parse tree, so that it will be called as parser also. So this parser is of two types. We are categorizing the parser into two types. So as we have already discussed, in the syntax analysis phase, we are generating the parse tree. So it is one type of a tree. So the tree can be constructed either from the root node to the leaf node or from the leaf node to the root node. So that is why we are categorizing the parsers into two types. That is top-down parser and bottom-up parser. In the top-down parser, the parse tree is constructed from the top to bottom, starting from the root node to the leaf node. So one of the example for this top-down parser is LL1 parser, brute force parsing technique, as well as LL1 top-down parsing technique. And under bottom-up parser, in this bottom-up parser, parse tree can be constructed from the leaf node to the root node. And LR parsers, shift reduce parser and LR parsers are the examples of bottom-up parser. And when we compare with these top-down parser and bottom-up parser, bottom-up parser will work efficiently. Why? Because if we are having, while we are constructing the tree, a particular node contains multiple alternatives, so that we may or may not choose a proper alternative production. At that time, if we choose a correct one, then it will be right. Otherwise, we may not be generate a parse tree, proper parse tree. That is, but if you go with bottom-up parser, we are constructing the tree from leaf node to the root node, so that if we combine the leaf nodes, whether we can form the parent node or not, that will be considered, and then we can construct the tree. If we are able to construct, we can construct. Otherwise, we cannot construct. So that compared to top-down parsing technique, bottom-up parser is more flexible. So next, as we have discussed, the parse tree can be constructed by using context-free grammar. Here, the context-free grammar can be defined by using 4 tuples. So here, NTPS. Here, N means non-terminal symbols. We are given with some set of non-terminal symbols in the grammar. And then terminals. T means terminals. And then P means productions. So here the productions are set of rules which can be specified by using terminals and non-terminals, so that by using these productions only we can generate the string from the given context-free grammar. And S is the start symbol. So for example, if the grammar is like A, so here A is a non-terminal. Every time the non-terminal can be represented by using uppercase letters, and terminals can be represented by using lowercase letters. So here it is a non-terminal, and set of terminals are, we may have set of non-terminals in the grammar. So here we are considering terminals, non-terminals, terminals, productions, and the start symbol. Here A itself is the start symbol, and we are having only one non-terminal symbol A. Now the productions are here non-terminal, terminals, and start symbol. Only we left with the production. So what are the productions we are having in the grammar, context-free grammar are A tends to small a, capital A, and A tends to ABC. These are the productions which we have given in the context-free grammar. In the same way, here in this grammar we are having S and F are the non-terminal symbols, 0 and 1 are the terminals. S is the start symbol. In the given non-terminals, we are having the S, right? So this S is the start symbol. Then the productions are S tends to 00S or 11F, and F tends to 00F or epsilon. So like this, we are having some set of productions. So the productions in themselves contains the terminals as well as non-terminals which are specified in the grammar. So by using the given production rules, we can generate the parse tree. So before going to generate the parse tree, we need to check whether we can generate the tree by using the given context-free grammar or not. We will be given with some set of in the grammar we are having some non-terminal symbols, terminal symbols, productions, and start symbol, right? But if we are given with a grammar like production rules as well as the input string, by using these production rules from the start symbol, can we generate the given string or not? That has to be identified. That is called as derivation. So if we are having, if we are given with the production rules, so that can we generate the tree? Can we generate the tree for the given input string or not? For example, here for getting that, we need to replace the non-terminal symbols with its production values. For example, if here alpha capital A beta is there, so this A can be replaced with gamma if we are having a production as A tends to gamma. So here, if we are in the given context-free grammar, if we are having A tends to gamma as a production, then this A can be replaced with gamma. In the same way, we need to replace all non-terminal symbols with the terminal symbols or terminal or its production rules, so that we can generate the parse tree. So this is one of the example for generating the parse tree. So while we are deriving the string from the given context tree grammar, we need to consider two things. One is leftmost derivation and rightmost derivation. What is meant by leftmost derivation is we should start in the context tree. We are given with the context tree grammar as well as the input string. Here the context tree grammar is S tends to S plus S or S star S or S star A. So here, and the given input string is A plus A star A. So that from that context tree grammar we need to derive the string. While deriving the string, in the leftmost derivation, every time the leftmost non-terminal symbol has to be replaced with its production. Whereas in the rightmost derivation, always the rightmost non-terminal symbol has to be replaced with its production. So see here the difference between leftmost derivation and rightmost derivation is, here this S has been replaced with A. Whereas here the last rightmost non-terminal, that is rightmost S, has been replaced with A. So that is the difference between leftmost derivation and rightmost derivation. So by using this either leftmost derivation or by rightmost derivation, we can derive the string. So the given context tree grammar is S tends to S plus S or S tends to S star S or S or A. So by using that, we need to derive A plus A star A. So either by using leftmost derivation we can derive. So here is S tends to. So S tends first we have taken S tends to S plus S, so that this leftmost S has been in the next iteration this leftmost S has been replaced with A. So first we have taken S tends to S plus S. Then this S as leftmost S has been replaced with A. Yes, this S has been replaced with A. Next we are having only one non-terminal symbol S that has been replaced with S star S. So here this S has been replaced with S star S. Whatever we are doing here, according to that only we are representing the tree. That tree is called as parse tree. Now this has been replaced with A. Next this S has been replaced with A. So by using leftmost derivation, if we derive the string, if we are able to derive the string, then according to this order only we are going to generate the parse tree. In the same way, in the rightmost derivation, first we will take the start symbol S, then we are taking S, suppose we can take either S plus or S star S. Now in the leftmost derivation we have taken S plus S, now I am taking S star S. Then this rightmost S has been replaced with A. Now this we are having only one S, so that one non-terminal symbol S, so that this S has been replaced with S plus S. We can take any of, why? Because this S is having four alternative productions. Any of the alternative production we can take. So now this S has, this is a in this case this S is a rightmost non-terminal symbol, so that has been replaced. Now only one S is there, one non-terminal S is there, now that has been replaced. So in both the cases, either it may be a leftmost derivation or rightmost derivation, we have derived the string A plus A star A, so that we can construct the parse tree either by using leftmost derivation or by using rightmost derivation. Now if we are able to generate the tree from the either by using leftmost derivation or by using rightmost derivation, those are two different things. If we are able to generate the tree only by using rightmost derivation, so that case is different. If we are able to generate only by using rightmost derivation, that case is different. If we are able to generate the trees in both the cases, either by using leftmost or by using rightmost, then it is that means the order of generating the nodes is different. But if we are able to generate more than one parse tree either by using leftmost derivation or by using rightmost derivation, that means if I want to make use of only leftmost derivation, but I can able to generate more than one trees only by using leftmost derivation, then it is called as ambiguity problem. Okay, so either I can go with leftmost derivation or rightmost derivation, but at a particular point of time we need to fix we are going with only leftmost derivation. Then also we are able to generate more than one leftmost derivation trees or more than one rightmost derivation trees. Then it is called as ambiguity problem. So if we are able to generate that, then and a confusion has been generated. That means in the compilation process, which tree has to be selected. So if it is leftmost or rightmost, we can select any one. But even though we are in a single state, that means either we are selecting only leftmost. So that also we are having two different ways. So which one has to be selected? That confusion has been generated. To avoid that confusion, we are having we can handle this ambiguity problem. So we'll take one example. What is ambiguity? Suppose if a statement contains if expression then statement, or the same statement may have if expression then statement else statement. That means a statement may be a simple if statement or if else statement. If in that case we can be able to generate multiple parse trees. That is to avoid that. That means we may get some confusion. To avoid that, we are having two techniques for avoiding this. Ambiguity problem. One is left recursion and left factoring technique. What is meant by left recursion and what is meant by left factoring is, if the production is having left associativity problem, then we can make use of left recursion technique. What is meant by left associativity problem is, if the production is in this format, the given production is in this format. What is this format actually? Here capital A is a non-terminal. Always non-terminals are having the productions. So that this non-terminal, whatever the non-terminal we are specifying here, the same non-terminal is there after the production. So arrow symbol is a production, right? So before the arrow, whatever the non-terminal symbol is there, after arrow also, if we are having the same non-terminal symbol, then we can say that it is having left associativity problem. To avoid that problem, we are rewriting this production as we need to make left associativity problem. To avoid this, we will make use of left recursion technique. So in this left recursion technique, how we are rewriting this production as, so the same production without changing its meaning, we are rewriting this production by eliminating left recursion. That means if the production is having left associativity problem, then by using left recursion technique, we are going to eliminate that problem. If the production contains left associativity problem, then we can easily say that it is having ambiguity problem. So to avoid that ambiguity, to eliminate that ambiguity, we are going to make use of this left recursion technique. So in this technique, we are rewriting the given production A tends to A alpha beta into this format without changing the actual meaning of the production. A tends to beta A dash and A dash tends to alpha A dash or epsilon. That means the single production has been reconstructed into two different productions or two different non-terminal symbols. So this is left recursion, and we'll consider some examples for this left recursion technique. So if the given production is A tends to A alpha or beta. So here we can, by seeing this production, we can easily say that this production is having left associativity problem. What is left associativity? A is before the production, whatever the non-terminal symbol is there, the same non-terminal symbol is there after the production. Then we can rewrite it as A tends to beta A dash and A dash tends to, here the alpha means after this A, whatever the symbol is there, that will be considered as alpha. So here not this only alpha we should not consider. Here after this start symbol, first symbol, whatever the symbols are there, all those symbols will be considered as alpha. Now the alpha become A alpha. But here this production is not having left associativity problem. Why? Because here the non-terminal symbol is A dash, but here the non-terminal symbol is A. So those two are two different symbols, so that we can easily consider, and there is no ambiguity problem. And the second problem is here we can take S tends to S0, S1, S or 0, 1. Now here this S and S both are same symbol, both are same non-terminal symbol, so that we can say that it is having left associativity problem. To avoid that, we need to rewrite this production as A tends to alpha, beta A dash. So here A is S, S tends to what is beta? Beta is 0, 1. 0, 1, what is A dash? So I am taking A as, instead of S dash I am taking A. Now this A will become A tends to, that means A dash tends to alpha. What is alpha? After this S, whatever is there, after this first character, whatever is there, that will be considered as alpha. Then that will be given as alpha, that is 0, 1, 0S, 1S and A dash. What is A dash here? A or epsilon. So this is one of the examples for left recursion, eliminating left recursion. We'll take one more example here. E tends to E plus T or T, T tends to T star F or F, F tends to E or I. So here, when we consider these three production rules, E, T and F are the non-terminal symbols, and we are having the three productions. Now, among these three productions, we need to identify what are the productions which are having the ambiguity problem. That means left associativity problem. So among these three productions, the first production is having left associativity problem. So why? Because this E, capital E is a non-terminal, and the same non-terminal symbol is there immediately after the production. So we can say that it is having left associativity problem. And the second production also, the non-terminal symbol T is there. Immediately after the production, again the same symbol is there, so that it is having left associativity problem. But in third production, there is no, here F is the non-terminal symbol, but ID is a terminal, and open brace is also a terminal, so that this production is not having any left associativity problem. So that for the first two productions we need to eliminate ambiguity. That means left associativity problem has to be eliminated. So we'll consider I'll take the same example. E tends to E plus T or P. Now this here I will consider A is equal to E. The production should be in the form of A tends to A alpha or beta. If the production is in this format, we can say that it is having left associativity problem, so that we should rewrite this production as A tends to beta A dash and A dash tends to alpha A dash or epsilon. So here for this I am considering this production, I am comparing this production with this production, so that in place of A we are having E. So A value is E. Next alpha is, after this E, whatever is there, that will be considered as alpha, so that it will become plus T, and beta value is only T. Now if this production is in this format, then we can rewrite this production in this, right, so that it will be, it can be rewritten as A tends to, here A value is E, E tends to, what is beta? Beta is T. Now T, A, beta, A dash, so T, E dash. Next A dash, here A means E, so that A dash means E dash. E dash tends to, what is alpha? Alpha is plus T. A dash means E dash or epsilon. So this is only for the first production. What about the second production? So the second production is T tends to T star F or F. So here both non-terminals are same, so that we can rewrite these productions as here A value is T and beta value is f. Here this is beta and star f is alpha, right? So this is a and this is a. Now beta a dash, f t dash. Next t dash tends to, that is a dash tends to alpha. What is alpha here? Star f a dash, that is t dash or epsilon. So in this way we can eliminate left associativity by using left recursion technique. Next, left factoring technique. So in this left factoring, first of all, if the given production contains same alternative production, that means previously we have discussed like a statement contains if, simple if as well as if else statement, right? In the same way, if we are having common values the all alternative productions, then we can make use of left factoring technique. For example, if we are having a production A tends to alpha beta 1 or alpha beta 2 or alpha beta 3, then alpha is common in all alternative productions of A. So here the thing is how we, the system gets confused that suppose if I want to derive a string, I should start with the first starting character. But thus in all the, so that if the starting character has been matched, then we can go with that particular production. But here the starting character is same in alternative productions, so that we cannot which one has to be considered, will get confused. That is why we are going for, to avoid this confusion, we are going for left factoring technique. So as previously we have discussed in the left recursion technique, in the same way without affecting the meaning or meaning, we are rewriting this production as A tends to A dash and A dash tends to alpha 1 or alpha 2 or alpha 3. So we'll consider one example here. In this example, A is common in all the productions. So we are writing this A commonly, this A is common and small a is common in all the productions, so that we are writing the same thing, and instead of AB or BC or AC, I am writing A dash. Now A dash value will be either AB or BC or AC. So in this way we are going to eliminate left factor. This is also one more example.